Hello everyone, it's Srinivas here, and today we will be solving an IGCSE Physics Paper 4, Variant 2 of the May June 2024 series. So let's start. For the first question, a load is suspended from a thread. The vertical force on the thread due to the load is 0.75 Newton. So we know that any force on the thread would just be because of the weight of the load. Since weight is a force that acts downwards, vertically downwards, so the vertical force on the thread would just be the weight. So we know the formula of weight to be W is equal to mg, where weight is W and m is the mass of the load and g is just the gravitational constant of 9.8 meter per second square. Since we already know the weight and we already know g, we can just rearrange the formula to be W by G is equal to M. So that would be 0.75 divided by 9.8 is equal to M, just 77 grams. So the answer would just be 77 grams. And remember to always maintain two significant figures in your final answers, because the minimum significant figure of the data provided in the question is two significant figures. So you should maintain a two significant figure answer in your final answers. Section B, figure 1.1 shows the load suspended from the thread. A wire is attached to the load at point X and pulled horizontally to the right. The tension in the horizontal wire is 1.2 Newton. By drawing a scale diagram or by calculation, determine the magnitude of the resultant of the force at X due to the load and due to the tension in the wire, the direction of the resultant relative to the vertical direction. Show your working. So since this is a vector diagram question and they've given us the option of by calculation, we can just proceed with the calculation, since that is much easier and more accurate to work with. So let's first visualize the setup. There is a force that is working horizontally from point X, which is a wire that's attached to point X and pulled. So it is pulled to the right. So there is a force to the right of X. And there is also an upward force on the actual thread, the vertical force, because there is a downward force of W. So since there is a force of W, there is also a force on the thread of that is equal to W. So since we already know W to be 0.75 Newton, we can just cut this out and we can just assume that the force on the thread is 0.75 Newton. And since we know that the tension in the horizontal wire at point X is also 1.2 Newton, we know that tension is a force due to the actual strain force on the wire. So when the wire is pulled to the right, the strain force on the wire would be equal to the force that's actually pulling the wire to the right. So the wire pulling the load to the right would just have a force of 1.2 Newton, since that's the tension of the wire. Since we know both of the values now, we can construct a right-angled triangle to find the magnitude of the resultant force. So first let's draw the horizontal vector, which is just 1.2 Newton. And remember to always touch the head with the tail of the next vector. So the other vector would just be this. Since it is there's a force of 0.75 Newton. Remember that the force here is moving upwards, since the tension on the thread due to the weight is moving upwards. So there would be an upward movement of the load, since there is always a force pulling it upwards at the same magnitude of the weight that's pulling it downwards. So the tension in the thread, which is actually the force acting here, would just be 0.75 Newton. Just make sure that you understand that. So once we've constructed the triangle, we can just draw the magnitude of the resultant vector. And using the Pythagoras theorem of right angle triangle, since this is a right angle triangle, we can just find C is equal to, which is C is just the resultant vector, C for the hypotenuse, just root of 1.2 squared plus 0.75 squared. So that would just be 1.4 Newton. So the magnitude of the resultant force would be 1.4 Newton. Now we know that the angle of the resultant relative to the vertical would just be this angle. Since this angle is the angle between the resultant vector, which is this vector, and the vertical vector, which is this vector. So this angle would just be tan theta, which is a trigonometric ratio that we use to find the angle using the opposite and the adjacent sides. So opposite by adjacent would be equal to tan theta. So tan theta equals opposite side is 1.2 Newton. So it's 1.2 divided by the adjacent side. So that is 0.75. So 0.75, and we can just take tan to the tangent to the other side. So that would be tan inverse of 1.2 divided by 0.75, which is equal to theta, which is none other than 57.99 degrees, or since we're keeping it at two significant figures for our answers, it's 58 degrees. So our answer is 58. Section C. Forces may produce changes in the size and the shape of an object. State two other changes that forces may produce. This is a pretty straightforward question. And forces are any push and pull that create a change in the motion or the change in the actual formation or conformation of an object. Conformation as in the size, the shape, and how much the twisting and everything. So other changes that a force may produce is in the actual motion. So the magnitude of the motion might change. So it can cause an acceleration because a force is just an acceleration. And other than that, it can also change the direction of the vector. So the direction can also be changed. So it can be direction. Other things that can be changed include the speed and the velocity, because when there is an acceleration, inevitably the speed and the velocity of the actual object might also change. Now we need to define acceleration. So acceleration is just v minus u by t, or delta v by delta t. Since delta v is just the change in velocity and delta t is per unit time, we can just write it as change in velocity per unit time. Since anything per unit time is also a rate, and it can also be described in the terms of rate, you can also say rate of change of velocity, or you can just give this equation A is equal to delta V by delta T, and they'll still give you the mark. But I would suggest this since it's the more refined answer, I would say. Okay, a train has a total mass of 520,000 kilograms. The train accelerates at 1.1 meter per second square. Calculate the time taken for the train to increase its speed from 15 meter per second to 28 meter per second. So we know that v minus u by t is equal to a. We know that v is the final speed, u is the initial speed, we know a is acceleration, and t is just the time taken. So rearranging this, t is equal to v minus u by a. We know v is 28, u is 15, a is just 1.1, and we get the answer as 12 seconds. And calculate the force required to produce an acceleration of 1.1 meter per second square for this train. So we know that F is equal to ma. M is the mass, acceleration is a. So m is just 520,000 into 1.1, which is the acceleration. So that's just 570,000 Newton. Since we're writing it two significant figures, just always remember to make it two significant figures. The train uses electric motors. Explain why the force on the train due to the motors is greater than the value calculated in 2. So, okay, realistically speaking, when a train is moving, being propelled by something, there is a force acting on it. The resultant force how we have calculated here is 570,000 Newton. So the force driving it, Fd, would also have some sort of friction that's acting to slow it down, which is, we can say it as air resistance. Since it is moving through the medium of air and air particles will collide onto the object, creating a friction, reducing the force output. So since 570,000 Newton is the resultant force, and it is only after Fd, which is the force of the electric motor, has been subtracted by the force of friction, of force of air resistance, is equal to 570,000 Newton. We can clearly see here that the driving force is greater than 570,000 Newton, since there is an extra friction, an extra air resistance that has not been considered in the scenario given. So we can just say there is air resistance. And the force is used to overcome this air resistance. So you can say which the additional force is used to overcome. Okay, the third question. A student drops a heavy ball from a vertical height of 1.8 meters from above the ground. The ball then falls to the ground. It does not bounce after hitting the ground. Describe the transfers of energy of the ball between stores from when the ball begins to fall to when it reaches the ground. Okay. First of all, the ball is standing some height above the ground. I'll use the red pen. Some height above the ground. Okay, when the ball falls down, there is some work done against gravity to take the ball to that particular height. Any work done against gravity is stored in the object in the form of gravitational potential energy. So this has some amount of GPE, or gravitational potential energy. Once the ball falls, this GPE is converted into kinetic energy, which is the energy associated with any form of movement. And when the kinetic energy of the ball is at maximum, which is around when it falls, right before it falls on the ground, you can also see in the question that it's clearly mentioned does not bounce. So once the ball hits the ground, all the energy somehow dissipates. It gets removed from the system. It moves into the surroundings. This is in the form of internal energy or thermal energy. So the kinetic energy is converted into internal energy. So if the first step is GPE is stored before ball falls, GPE is converted into kinetic energy, increasing is a key word here because the kinetic energy has to increase, shown by the actual increase in speed of the ball as it falls down. So increasing Ke, or kinetic energy, and this kinetic energy is transferred to thermal energy once ball hits the ground, since it needs to dissipate. Okay, Now let's calculate the maximum speed of the ball and ignore air resistance. So we already know that v square is equal to 2gh. This is derived by the formula half mv square is equal to mgh. We know that all the kinetic energy is equal to the maximum amount of GPE that's stored inside the ball when it's before it's falling down. Since m is common on both sides, we can just cancel m. We know we can take 1 by 2 to the other side, so it's v square by 2gh. Okay, now we know the height, so the height is just 1.8 meters, so v square is equal to 2 into 9.8 into 1.8. So v is just root of 2 into 9.8 into 1.8, where the answer is 5.9 meter per second. And one more thing that you need to mention in this question is that the EP, or EP is just GPE, is equal to the EK gained, as in the kinetic energy gained. You can also show it via this equation here, but it is always better to mention it in the form of a statement to show your understanding to the examiner. 5.9 meter per second. Since it's speed, it's meter per second. Okay. Fourth question. State two ways that evaporation differs from boiling. Okay. The first thing evaporation differs by is that it only happens at the surface. It is only a surface phenomena. So only happens at surface, whereas boiling is throughout the liquid, and it's like happens throughout the liquid. Okay, and evaporation doesn't need a certain temperature like boiling, which requires a boiling point, a specific temperature, which is required for the atoms and the molecules to break apart from the intermolecular forces and become a gas. However, evaporation happens in a series or a range of temperatures. So it is, yeah, it happens in a range of temperatures because it's only at the surface. Particles that have slightly higher energy than the other particles escape in the form of gas, cooling the whole of the liquid down. So the evaporation only happens at the surface. So it is a range of temperatures. Range of temperatures. Whereas boiling only happens at the boiling point. And that's something to keep in mind. Okay. Figure 4.1 shows part of a container used to store a mixture of liquid and gaseous oxygen. The temperature of the liquid oxygen is minus 160 degrees Celsius. Determine the temperature of the liquid oxygen in Kelvin. So Kelvin, T in Kelvin is always equal to T in degrees Celsius plus 273. So it's minus 160 plus 273, which is 113 Kelvin. Since this is an exact value and we're using 273 as the value that we're adding it by, we can keep our answer at three significant figures because it is still something that we're using to be exact. It is something that needs to be exact since we're using an exact value of 273 to find the Kelvin value. Okay. The container is made of steel and there is a vacuum between the inner and outer walls. The outer wall of the container is at room temperature. State two methods of thermal energy transfer that a vacuum prevents. Okay. There are three methods of thermal energy transfer: conduction, convection, and radiation. Okay, so conduction happens via contact, hence the name conduct. It happens when two things are in contact to each other, when two objects of different temperatures are in contact with each other, and the particles collide with each other, causing a vibration in the other object, making temperature to move from the higher temperature area to the lower temperature area until there is a constant temperature. Whereas convection happens due to the density differences in the fluids. When a particular section of a fluid, such as liquid and gas are both considered fluids, when a particular section of liquid or gas becomes hotter, it becomes more dense. So the higher density causes this section of the liquid to rise up, whereas the cooler fluid on the top comes back down. So this cycle keeps repeating, whereas the liquid at the bottom gets heated up, moves upwards, the cooler liquid comes back down. So this keeps occurring until there is a constant temperature at the top and the bottom. So this is known as a convection current, and this also requires some sort of fluid to be present. Whereas radiation only happens solely through electromagnetic radiation. Electromagnetic radiation, such as infrared and microwaves, can cause molecules to start vibrating and cause an increase in the temperature. Since temperature is just the average kinetic energy of the molecules, when the molecules start vibrating, the average kinetic energy of the particles increase, causing the temperature to increase. So the two methods of thermal energy transfer that a vacuum prevents are just conduction and convection. Since conduction requires contact between the inner and outer walls to transfer, whereas a vacuum prevents that, and convection requires a fluid to move, such as whereas one side gets hot, it moves up, the one side gets cold, moves down until a temperature gradient is balanced. So conduction and convection are the two things that are prevented, whereas radiation can happen via even vacuum, since it is just electromagnetic radiation, and electromagnetic radiation does not require any medium to pass through. Okay, now describe in terms of particles how a gas exerts a pressure on the walls of its container. This is a very important question in IGCSE physics because it's a very common question. It's repeated quite a lot. So you can imagine, first we would start with why a force actually gets applied on the wall. So first of all, gas particles keep moving. They move a lot. They randomly move and they collide with the walls of the container. So that's the first point. Particles collide. Collide is a keyword with the wall of the container. Secondly, these particles, when they collide, they cause a change in momentum, or they exert an impulse on the walls of the container. Or you could say they exert a force on the wall, since the rate of change of momentum is just force. So when a change of momentum is exerted on the wall on a period of time, a force is exerted on the wall. Since the particles keep colliding and there is a sort of pushing force exerted on the wall. So particles exert a force on the wall. Okay. And now we know that the force is exerted. So force divided by the area of the wall is just pressure. So pressure is just force per unit area. So since there is a force over a unit area is pressure. So since there's a force, there is a pressure acting on the walls of the container. So these 3 points are very important. First, the particles collide. They cause a rate of change of momentum, exerting a force on the wall, and that force per unit area is just pressure. So a pressure is exerted on the walls of the container. Okay, fifth question. Figure 5.1 shows a ray of yellow light incident on a glass prism ABC. Explain why the ray does not change direction when it enters the prism at face AB. Refraction happens when there is an angle of incidence, when there is an angle of refraction. Okay, so when there is no angle of incidence, since this is directly perpendicular to the boundary, it is directly perpendicular to the boundary, and it is parallel to the normal. It directly falls on the normal of the boundary. So the ray is perpendicular and travels along the normal. And you can also say angle of incidence. I'm using the short term, but remember, sorry, okay. Remember to always write angle of incidence. Do not write the symbols, but I'm using it here. Angle of incidence is equal to 0 degrees. So since the refractive index is just sin I by sin R, because the angle of incidence here is 0 degrees, there is no angle of refraction as well. So there's no bending. Okay, the critical angle for the glass is 42 degrees. Calculate the refractive index of the glass. Okay, so we know n is equal to 1 by sine c, and this is uh, this is derived via the formula n is equal to 1 by n is actually equal to sin I by sin R. Why we're taking 1 by n here is total internal reflection only happens when light is moving from a denser medium to a rarer medium. So when the boundary, for example here, glass is the denser medium, and air here is the rarer medium. So when the boundary is just the boundary between the denser medium and the rarer medium, only there does total internal reflection actually occur. So since there is total internal reflection here, we are taking the formula for the denser to rarer method, which is 1 by n is equal to sin I by sin R. So we know that is equal to sin R by sin I. We know sin R right on the critical angle would be parallel to the boundary. So right on critical angle, this light would just travel along the boundary like this. So angle of refraction would just be 90 degrees, since it is traveling along the boundary, parallel to the boundary. Sin R or sin 90 now, and the incidence angle is just a critical angle. So sin 90, we know sin 90 to be 1. So that would just be 1 by sin C is equal to n. So that's how this formula is derived. This is not necessarily needed for the IGCSE exam, but it's good to have a basic understanding on what it says. Okay, I'll just erase that. Okay. And n is equal to 1 by sin c now. So we know critical angle is 42 degrees. So n is equal to 1 by sin 42, which is just equal to 1.5. Since refractive index is just a ratio between the speeds in the denser medium and the rarer medium, there is no unit since it's just a ratio. Okay, on figure 5.1, continue the path of the light through the prism and after it leaves the prism. Okay, here you can see that this angle is the angle of incidence here is greater than 42 degrees. So when the incidence angle is greater than the critical angle, you would have total internal reflection. So this would reflect with a reflected angle of 42 degrees. So this is also 42 degrees. Make sure that you're actually measuring that. And once this hits AC, there is no angle of incidence. So this would actually be moving something like this, since that is the proper 42 degrees. So you can see that this is parallel to the normal, like you see here. This is parallel to the normal, and when it is parallel to normal, there is no angle of incidence. Angle of incidence is equal to 0. So that would just pass straight through the air. So that's how you draw the diagram. Okay. Internet data can be transferred using infrared waves in optical fibers. State 2 advantages of using optical fibers to transmit data. Okay, optical fibers work via the mechanism of total internal reflection, where it passes infrared waves through the optical fibers, which are something like this, and they get reflected along the internal surface and move. This ensures that there is high quality of data transmission. There is no loss. There is virtually no loss, and this means that the data can be transferred very effectively, very quickly, but also with high quality. And that's what enables internet as we know it nowadays. Okay, so the first advantage would be high rate of data transmission or fast data transmission, because you can see that infrared waves are electromagnetic waves and they travel at the speed of light, which is the maximum attainable speed in the known universe right now. Okay, so high rate of data transmission. This is the maximum speed, so it is the fastest we can transfer data by. Also, it can also do it with very low data loss. It is little data loss. There is virtually no data loss and it's very high quality. That means it can transfer large amounts of information with little data loss and high rates. So it can also transfer, some other points would be large amount of data and also secure. The secure point is slightly more complex because you can see that when we pass infrared like this at an angle that is not the critical angle, or we pass it directly, it will not interfere with the light inside the optical fiber, and it will not travel inside the optical fiber as well. This means that no one can intercept the optical fiber signals and send their own infrared waves via the optical fibers. This means no one can interfere with the the data that is traveling by the optical fiber. So it is almost it is very secure. It's very hard to hack into it and make your data much more secure as well. So glass is transparent to the infrared, but when it travels inside the optical fiber, it works via total internal reflection. So it's very hard to hack. Okay. A sound wave travels through air. Figure 6.1 shows a pressure time graph for the air at one place. Okay. Pressure time graph is to be noted here, because pressure means it's not displacement anymore. Displacement would show that it's actually a transverse wave. This is not displacement. This is pressure. Pressure indicating a longitudinal wave, and also it's a sound wave, so it's a longitudinal wave. On figure 6.1, label 1 point C to indicate a compression. So a compression is a place where pressure is the greatest. So you can just label it on the part where there's the greatest pressure. So the crest C, excuse me. And you can label R on the place with the least pressure. So a compression is the place where the greatest pressure, and rarefaction is the place with the least pressure. So something like this. Imagine these are wave fronts, and they get concentrated here and they get relaxed here. So this is a rarefaction, this is a compression, this is again a rarefaction. So this would be R. Explain why this graph cannot be used to find the wavelength of the sound wave. Why the wavelength of the sound wave cannot be explored here is that this is a graph with time in the x-axis. So that means there is only the variation along time. So you cannot really find the distance between adjacent crests, adjacent troughs using this method, since there is no way of finding the displacement between each of the crests and the rarefactions. Okay, so that means this graph cannot be used to find the wavelength, since there is no variation along displacement. So the graph does not show displacement. Okay, the sound becomes louder and of lower pitch. State what happens to the amplitude of the sound. Okay, when a sound becomes louder, the displacement of the particles becomes greater. The maximum displacement is greater, and that means the amplitude of the sound is also greater, since amplitude is just the maximum displacement of the particles from the mean area. So the amplitude of the sound would just increase. And the frequency of the sound would decrease here, since the frequency of the sound directly is proportional to the pitch of the sound. So when there's a lower pitch, there's a lower frequency. A sound of frequency 13 kilohertz is transmitted through water. The speed of sound in water is 1500 meter per second. Calculate the wavelength of the sound in water. Okay, we know V is equal to lambda F, where lambda is the wavelength, frequency is F, and V is the velocity of the wave. So we know the speed is 1500, we know lambda is wavelength, and we know frequency is 13 kilohertz. So that means 13 into 10 to the power 3 hertz. So that's 1500 divided by 13 into 10 to the power 3, which is equal to 1.2 into 10 to the power minus 1, or 0.12 meters. Okay, state the approximate speed of sound in air. It is 340 meter per second, but you can give any value between 330 and 350. 340 is more safer, since it's been followed for multiple years of IGCSE. For IGCSE from a long time, we have been stating is 340 meter per second, whereas in the new syllabus given 330 to 350. But it's just better to go with 340, since that's what's been followed for so many years now. The seventh question. Figure 7.1 shows three bars of steel, A, B, and C. A student is given the three pieces of steel. Two of the pieces are magnetized and one piece is unmagnetized. Describe and explain how the student determines which piece is unmagnetized using only the three pieces of steel. Okay. When two pieces are magnetized, they would have a north pole and a south pole. Like poles repel and unlike poles attract. So that's one thing that you need to keep in mind here. When the other piece is unmagnetized, but it's still steel. Steel is a ferromagnetic material. It is a magnetic material which would attract to any side of the magnetized steel. So first, what you would do is you would bring one of the pieces of the material to the other piece, and you would see that if both of them attract on both sides, one of them is unmagnetized. You understand? Since, for example, C is the unmagnetized one and you bring A next to it. No matter A has north here or south here, or south here and north here, C would still attract, since it is an unmagnetized material and it would magnetize either way and still attract. However, for example, if B and A were the magnetized pieces, if I brought B here, B had N and S and A had N and S, this would attract. However, in the opposite direction of N and S, they would repel. you see, they would repel. So this means that the pieces can be figured out if they are unmagnetized when they attract to both sides of the magnetized piece. Okay, so how do we formulate a method with this? First, we check how we're bringing each together. So first we bring each piece together to the other piece. Bring, okay, and check if there is attraction or repulsion on both sides. If there is attraction on both sides, if there is attraction on both sides, it is magnetized. Sorry, unmagnetized. One of them is unmagnetized. Attraction on only one side, that is magnetized. Now we know the boundary conditions for finding if two pieces are magnetized or unmagnetized. So we just repeat this test for different pieces, checking different combination of the pieces. And once we check the different combinations, at the end we would be easily able to understand which one is the one that's magnetized or unmagnetized. Since the unmagnetized one would attract on both sides to the both of the magnetized one, and the magnetized ones would repel each other when positioned, and on one orientation they would attract each other, similar to what's shown here. So yeah, okay. B. Figure 7.2 shows a circuit diagram. Sorry. Figure 7.2 shows a circuit diagram of a step-down transformer. The mains voltage supplied to the transformer is 240 volt. The output power of the transformer is 45 watt. The transformer is 100% efficient. Calculate the input current to the transformer. Okay, we already know that IP VP is equal to IS VS, right? We already know that. So when we substitute into this equation, okay, sorry. Okay, we already know that the mains voltage supplied here is 240, and we know that the output power would just be 45. So the output power of the transformer would equal the input power. So 240 would equal 45 into some IP. So that means IP is just 45 divided by 240. So this is the opposite way. Power is equal to V into I. We know the output power is equal to the input power. So output power equals the input power. So we know P is equal to VI. So we know the output power is 45. So the input power is also 45. Since in a transformer, even though the currents change and the voltage change, the power is what is transferred between one coil to the other coil. The power is what is transferred. Since the power is what is transferred, that's why when we change the voltage, the current reduces, and when we increase the current, the voltage reduces. So 45 is equal to 240, which is the the input voltage, and IP, which is the current in the primary coil. So it's 45 divided by 240, which is equal to 0.19 ampere. Remember to keep the two significant figures. And draw a label diagram of step-down transformer. On the label, state a suitable material for each of the components. Okay. Since this is a step-down transformer, the secondary coil has to have fewer coils than the primary coil. Since a fewer coil setup means that the voltage would reduce and the current would increase. Okay, so first we draw the soft iron core frame. something like this. This is the iron core frame, and this is what links the magnetic flux of the primary coil to the secondary coil. So transformer works by linking the primary coil and the secondary coil and the magnetic flux. Magnetic flux is the rate of change of the magnetic field between the two coils. So when there's a rate of change of magnetic flux on one coil, the current in the primary coil is transferred to the secondary coil. And the soft iron core is just for efficient linking. So we draw the primary coil, which has some number of coils, sorry. Okay, and this has 1, 2, 3, 4, 5, 6 coils. So we can just draw 3 here. So the secondary coil, so this is copper. So both of these are copper coils. Since we have to mention it's copper, since copper is one of the best conductors in easily sourceable conductor as well, and since it's one of the best conductors and it's capable of conducting current very well, it also has a high magnetic flux capacity as well, which means that it can have a more heavily generated magnetic field around it. So copper coils are used on both sides. This is a soft iron core. Sorry, soft iron core. Soft is to be mentioned, meaning soft iron core means that it can be magnetized and demagnetized very easily. Soft iron core is very important here since we don't want the iron core to be permanently magnetized because of the magnetic fields acting here. We want it to be only um, temporarily magnetized, only when the current is flowing. So the soft iron core enables it to be magnetized for a short amount of time and quickly be demagnetized once the current is turned off. And yeah, this is the primary coil. Just mention that it's copper coils too, and secondary coil. And that is the, and when, remember that is a step down transformer, so the primary coil would have greater number of turns and the secondary coil would have less number of turns because a high voltage is converted to a lower voltage. Okay, now figure 8.1 shows a circuit. The circuit is designed to switch on a night light when the surroundings are dark. On figure 8.1, draw the circuit symbol for a voltmeter used to measure the potential difference across the light-dependent resistor. Voltmeters are always connected. They're always connected in parallel, and the light-dependent resistor, the LDR, is this one. So we can just connect a voltmeter here, which would actively measure the voltage across the LDR. Since voltmeters have, I would say, a theoretical voltmeter has a very high resistance or an infinite resistance per se, which prevents any current from passing through this coil. The current only passes through these two coils. This F allows it to measure the voltage across the resistor since there's no current passing through it, and it also allows it to do this without damaging or without changing or altering anything that's happening in the original circuit. So this high resistance path makes it so that the electrons choose to flow through this path and this path rather than taking the voltmeter path. That's something to keep in mind. And the surroundings change from light to dark state. The effect of this change on the resistance of the LDR. So this is a NTC resistor, which is a negative temperature change resistor. So when there is a change from light to dark, the resistance of the resistance of the LDR increases. when there is a change from light to dark, the resistance increases. So it is an inverse proportionality with the light intensity. When the light intensity reduces, the resistance increases. Okay. State and explain the effect of this change on the PD across the light emitting diode. Okay. First, when the resistance increases in a series circuit, the voltage across the resistor with the greater resistance increases. So the key word is greater proportion. So greater proportion of voltage across greater voltage or total PD. Total PD as in total potential difference across the LDR. Since the LED is connected in parallel with the LDR, there is also a greater proportion of voltage across the LED. So also across LED. This means there is a greater current now passing through the LED. Greater current passing. Since the voltage is increased, the current also increases. Which causes LED to glow. And this is how it looks. This is because the LDR has a greater resistance now, and since it has a greater resistance, it has a greater proportion of the total PD split across it. The LED also now, since it's connected parallel with the LDR, has a greater potential difference across the LED now. This greater potential difference means there is a much stronger current now passing through the circuit here rather than here. This greater current causes the LED to glow more brightly. And that's about it. Okay. Figure 8.2 shows another circuit. Lamps A and B are identical filament lamps. The current supplied by the power supply is 0.5 ampere. Calculate the resistance of lamp A. Okay. So first, let's find the total resistance of this setup here. So V is equal to IR. We know 240 divided by 0.5 ampere is the total resistance, which is 240 divided by 0.5 is 480. And we know that 480 is the total of this entire setup. So the resistance of A, we can just take it as R, and this is also the resistance of B is also just R. So R into R by R plus R is equal to the total resistance, which is 480. So R into R is R squared divided by 2R is equal to 480. And we do a little bit of math and we just get that this is half of the total resistance. Since when two lamps are connected in parallel with each other, when they are connected in parallel with each other, both of them have half of that initial resistance. So this entire setup has half of the initial resistance. So half of initial resistance is equal to 480. So 480 into 2 is equal to 960 ohm. So 960 ohm is the resistance of lamp A. Okay. Yeah. Now the ninth question is radioactive isotopes that emit ionizing radiation are used in hospitals. State and explain two safety precautions necessary for the use of these isotopes in medical procedures. Safety procedure 1. The radiation is quite harmful for people, and it has the capability of breaking your DNA and replacing it with mutations. So the increased number of mutations could cause a cell to become cancerous, and that is obviously quite bad. So the first thing that you can do is to reduce the exposure time. The explanation for this is that there is a lower actual amount of radiation. Since you're exposed to it less, there is lower amount of radiation being observed in your body. And other than that, you can also use shielding. If you've noticed, if you've gone into an X-ray theater before, the X-ray technician, they always wear this lead ID card or this lead tag or lead-lined vests when they are working with the radiation. This lead-lined vest, since lead is a very dense metal, it prevents the radiation from passing through the vest into the person's body. So this prevents the exposure, this prevents the absorption of the radiation into the person's body. So you can use lead lined suits, or you can use something like that. So the explanation for this, it cannot penetrate. So the radiation cannot be penetrated and blocked. Okay. Give two reasons why alpha emitters are not used as radioactive tracers inside the body. The first thing is radiation would not actually reach outside of the body. Since alpha emitters and alpha particles are very heavy particles, they move very slowly, they interact much more often with the molecules around them. So this interaction makes them quite reactive and reduces their penetration power. So radiation would not reach outside. Secondly, the actual radiation would be much more dangerous for us. Since alpha emitters are more slow, they're more massive, they would have a much more drastic effect on our body. They would have a much more ionizing effect in our body, since they react with the surrounding media and the surrounding atoms, molecules much more frequently. This causes more ions to be released, since what alpha particles do is they collide with the atoms, knock out the electrons, forming ions. These ions can go then interact with the bodily systems that we have. Sorry, interact with the bodily systems we have, and actually disrupt them. So high ionization, which is quite bad. Okay. Sodium 24 is an isotope of sodium that has a proton number of 11 and a nucleon number of 24. Sodium 24 decays by emission of a beta particle to form an isotope of magnesium. Use nuclide notation to write down the nuclide equation for this decay. Okay. First we have to write the actual sodium isotope, which is just 24Na11. 24 is the nucleon number, and we know sodium has a proton number of 11, so it's 24Na11. So when something decays via a beta particle, what happens actually is a neutron actually forms an electron and a proton. The neutron splits into an electron and a proton. So that means the number of electrons in the number of protons in the actual nuclide would increase. So that would be, and the number of neutrons would reduce. So since there's an increase in the number of protons and a decrease in the number of neutrons by 1, the actual mass number remains the same. Since mass number is equal to number of neutrons plus protons, and plus 1 and minus 1 cancel out. So it's just 24 mg, 12 though, since there is one extra proton plus the actual beta particle. So that is 0, minus 1, beta. Minus 1 because it has an electron rather than a proton, so it has a minus 1 proton, since an electron is basically a negative variant of the proton. So it says 0, -1, eta. And that's pretty much it. Okay. 10a. The solar system includes the sun and planets. Sorry. State two other types of natural objects that orbit the sun. One of the other things that orbit the sun are the asteroids in the asteroid belt, positioned between the actual position between Mars and Jupiter. It contains lots of asteroids, and that is another thing that rotates around and orbits around the sun. Another thing that orbits around the sun are comets. Comets form a highly eccentric orbit or an elliptical orbit, meaning that they have two foci. Similar to this is diagram here, they would have another foci around here. So that's also another thing that orbits the sun. So a comet. Another thing that orbits the sun is dwarf planets such as Pluto, Ceres. Those are all dwarf planets that orbit the sun, and those are also other celestial objects that orbit the sun. Okay. State the shape of the orbits of the planets. Remember, it's always elliptical. It is never circular, and that is proven by the Kepler's law. And we don't have that in the IGCSE syllabus, but it is proven by the Kepler's law that orbits are always elliptical; they're not circular. Okay, figure 10.1 shows the orbit of an object around the sun. At point A, the object is closest to the sun. At point B, the object is furthest away from the sun. State and explain the energy transfer as the object travels from point A to point B. Okay, the first thing to consider here is throughout the orbit, the total amount of energy never changes. So the total amount of energy here and the total amount of energy here and the total amount of energy here never change. The total amount of energy at every point in the orbit remains the same. The total amount of energy as in the amount of gravitational potential energy and the amount of kinetic energy processed by the object. However, these energies do get interconverted, I would say. So when it moves from A to B, B is at a higher distance from the sun. This higher distance means that there is greater work done against gravity. So this greater work done means that there is high GPE here. GPE again just being energy that is caused by the work done against gravity. And when it moves closer to the sun, the gravity of the sun actually pulls the object towards it very quickly. This force increases the speed of the object, meaning that the object travels much faster and has a higher kinetic energy next to the sun. So when it moves from A to B, the Ke decreases and Pe or gravitational potential energy increases. You could say potential energy or you could say gravitational potential energy. And the explanation is that sorry, energy is conserved. Why I'm using the term conserved here is the law of conservation states that energy can only be converted between two forms. It can neither be destroyed nor created. So the Ke and the Gp is never lost, truly lost. It's only converted into the other form. So it's either Gpe or it's again converted to Ke. So the total amount of energy is always conserved, as in it remains the total amount of energy always remains the same. Okay. Jupiter is 7.8 into 10 to the power 11 meters away from the sun. The speed of light in a vacuum is 3 into 10 to the power 8 meter per second. Calculate the time taken for light from the sun to reach Jupiter. So that's just V to D by T. We know V, we know D, so it's D by V is equal to T. just 7 into, 7.8 into 10 to the power 11 meters divided by 3 into 10 to the power 8, which is just 2.6 into 10 to the power 3 seconds. So it's 2.6 into 10 to the power 3 seconds. 11a. Name the galaxy that contains the sun. This is quite straightforward. Milky Way galaxy. It is the galaxy that contains us, and the closest galaxy to us is the Andromeda. Light observed from distant galaxies is redshifted. State the theory of the universe that this observation supports. Okay, this supports the Big Bang theory, since the Big Bang theory states that the universe started from a tiny point known as a singularity, and then it's Big Bang, not Big Bang. The Big Bang theory, and it states that the singularity exploded and the universe has been expanding ever since. So this expansion of the universe means that the frequency of the galaxies, the light that the galaxy produces, becomes redshifted. This is known as Doppler's effect, meaning that the wavelength becomes further and further apart as the galaxies move away from us. This means that the apparent wavelength of the light produced increases and the frequency decreases, causing the light to become redshifted, as in move to the red spectrum. Okay. Cosmic microwave background radiation is observed at all points in space. State when this radiation was produced. So it was produced when the universe was formed. So shortly after the universe was formed. It's important to write shortly here, since it's not formed directly when the universe was formed. It is formed from the actual reactions that happened shortly after the universe was formed, where the hydrogen started reacting with each other, nuclear fusion and stuff like that has started happening. Okay. Explain why this radiation is now in the microwave region of the electromagnetic spectrum. The first point is that the universe has expanded. Okay, so imagine this to be the source of the radiation. Once the universe has expanded, this radiation started to increase in wavelength asymmetrically on one side alone. This is because the total section of the universe has expanded. This means that the universe has now expanded, and the actual radiation that's produced has been redshifted, similar to what I explained in the earlier case. But the problem now is that it has been expanding for so many years now that the radiation has been redshifted by so much time that the radiation has now eventually reached the microwave region, from gamma rays to X rays to ultraviolet to the visible region, and then into the infrared region, and then finally into the microwave region. So from gamma rays, which was originally produced by when the universe was formed, it has been slowly redshifted, whereas where the wavelength has kept on increasing and the frequency has kept on decreasing, and it has stepped down in the electromagnetic spectrum slowly, one by one, into the microwave region. So the radiation has been redshifted. And yeah, that's about it for this question paper. I hope this was helpful, and yeah, that's it for today's video, and I hope to see you again next time soon. Thank you and bye.